Hello, this is Jude Socrates, and welcome to a portrait of linear algebra. Today's video is about a general determinant formula. So, in our past couple of videos, we saw a way to compute the determinant of a 2 by 2 or a 3 by 3 matrix. So now we finally get to see a formula and a method by which we can find the determinant of any n by n matrix. So that is, of course, our first goal, to see the general formula for the determinant. And from this formula, we can derive basic properties of that formula. Now, it shouldn't be a surprise to you that we will be using elementary row operations to find the determinant of a matrix. But here's the surprise. We will also now be allowed to use column operations. So that is something new, and we'll see that very soon. Okay, so here is the formula for the determinant of an n by n matrix. It fits into one line, but obviously there's a lot going on in that one line. So, as usual, let Aij be the entry in the matrix A in row I, column J. Okay? So what is the determinant of A? It is expressed as a summation, although it's a different format of what you usually see in a summation formula. Usually it's summation I equals 1 to n or something like that. Here, under the summation sign, we have all n factorial permutations sigma of 1 through n. What goes into the summation? Well, first you get the sign of sigma, and then you take the entry in row 1, column sigma 1, and then the entry in row 2, column sigma 2, and so on, until you get the entry in the last row, row n, column sigma n. You take all of those n terms and the sign, plus or minus, multiply that out. That is one term in this formula. There are n factorial permutations, so there are n factorial terms in this formula. So you take all of those n factorial terms and then you add them all together. So obviously that is a cumbersome way to compute the determinant. For a 4 by 4, 4 factorial is 24. Okay? So you will have 24 terms. You will have to multiply them out, and then you have to add them all together. That's a lot of work, and that's not a practical way to do it. Okay? But let's start to understand this formula. So for each term that we want, what do we have to do, basically? Well, we can think of it this way. Pick an entry from every row, but as you do that, you also have to pick an entry from every column. All right, and why is that? A permutation is a bijection. So in other words, every column number also has to appear exactly once. We can see right away that the row numbers appear exactly once, but the permutation here guarantees that the column numbers also appear exactly once. Now, once you have all of the terms that you want, you can form the permutation of the columns that that term produces. Get the sign of that permutation, and then you can multiply all of those numbers together. Okay? I did not change the formula. Okay? I just thought of it in a different way. Okay? But now, let's investigate that formula a little. Okay, so here is a 5 by 5 matrix. And I am picking out an entry in every row and in every column. So double check. Row 1, row 2, row 3, row 4, row 5. Okay, exactly one entry in each row, but also column 1, column 2, column 3, column 4, column 5. Exactly one entry from each of the 5 columns. Okay, so what is the term corresponding to this? Okay, so I'm going to have a sign of a sigma, and then I will have this product. Okay, so I will have A13, I'll keep the box. A13, A25, A34, A41, and A52. Okay? So, who is the sigma? It is the permutation 3, 5, 4, 1, and 2. Okay? So now, let's count the inversions in that permutation. Okay? So before we list them out, let's just count them in an organized way. 3 is bigger than 1 and 2. So we have 2 inversions produced by 3. 5 is bigger than 4, 1, and 2. So we have 3 inversions in 5. 4 is bigger than 1 and 2. So we have 2. 1 is not bigger than 2. The last entry never contributes. So we have a total of 7. 7 inversions. So the sign of sigma is, of course, -1 because 7 is off. Okay? So therefore, the final contribution of this term is the negative of this product. Okay, so based on this formula, what is the first thing that we can conclude? Well, something very easy. If one of the rows of your matrix is entirely made up of zeros, then the determinant is simply 0. Okay, this one's a no-brainer. Okay, so we saw that you have to pick a number from every row and every column. So there is no avoiding row 4. You must pick an entry from row 4. So therefore, each term is going to collapse to 0. So the sum of all of those terms is exactly 0. All right, so I mentioned that we will eventually be able to perform column operations on our matrix as well. So to prepare for that, we are going to rewrite the term that we got in a different way. So what do I mean? The terms are arranged so that the rows are in increasing order. Okay? What if we rearrange it so that the columns are in the correct order, increasing order? So this is the entry from column 1. This is the entry from column 2. And then there you are, from column 3, the first factor, and then column 4, there we go, and column 5. Okay, however, we now have a permutation of the rows. Okay, the columns are in correct order. Now it's the rows which are in a wrong order. So who is that permutation? Let's call it cap. Okay, so that's 4, 5, 1, 3, 2. Okay, so I saved the sigma that we got from our previous computation. How is this tau, though, related to sigma? It's not very obvious, is it? Okay, but let me point it out to you. In sigma, 1 goes to 3. Where does 3 go to? Oh, it goes back to 1. In sigma, 2 goes to 5. Where does 5 go? Ooh, back to 2. 3 goes to 4. 4 goes back to 3. 4 goes to 1. 1 goes back to 4. 5 goes to 2. 2 goes back to 5. That tau is simply sigma inverse. Okay, and what did we say in the last video? We said that the sign of sigma inverse is exactly the same as sign of sigma. Okay, so this tells us that we can rewrite the formula for the determinant of the matrix so that this time the columns are in increasing order, and then we write down the permutation for the rows this time instead of columns. And since that permutation is simply the inverse of the original permutation, we get exactly the same sign. So therefore, the formula adds up to the same determinant. All right, so let's formalize that. We can rewrite the determinant formula as the summation over all n factorial permutations sigma of 1 to n. You still have the sign of sigma, but this time you write the terms as a sigma 1 column 1, a sigma 2 column 2, and so on up to a sigma n column n. So what we get is exactly the same determinant. Okay, so here's a property which is basically proven using exactly the same idea. We're going to transpose a matrix. And remember, when we do that, a row becomes a column and a column becomes a row. So it shouldn't be a surprise that if A is an n by n matrix, then the determinant of A is exactly the same as the determinant of A transpose. Okay, so why is that? Here's a matrix, and I have chosen the entries A13, A22, A34, A41. Again, exactly one entry from each row and one entry from each column. Exactly one. Transpose that matrix. So row 1 becomes column 1. Okay, row 2 becomes column 2, and so on. Where do the box entries go? A13 is now in column 1. A22 stays in column 2. A34 is now in column 3. And A41 is now in column 4. Okay, so why is the determinant of A transpose, which we will call B, exactly the same? So this is one term in our original determinant. So we have from A, we have the term A13, A22, A34, and A41. And we still have the sign of sigma. Okay, who is sigma? Okay, so that is the permutation 3, 2, 4, 1. Okay, now how about from B? So from B, we will have the term A41 from row 1, A2 from row 2, A13 from row 3, and A34 from row 4. Okay, however, I used the original formula where we get the permutation of the rows to make the determinant for A. Okay, how about for B? Well, I should still use the same formula so that we can compare the two fairly. Okay, so that means that I need to get the permutation tau from these entries. Okay, now what do we have to do? We kind of have to squint a little bit, okay? Because we have to extract the column numbers from this term, okay? So from row 1, we pick column 4. From row 2, we pick column 2. From row 3, we pick column 1. From row 4, we pick column 3. Okay, so before, tau was sigma inverse. Is it still sigma inverse? 1 goes to 3, 3 goes back to 1. 2 goes to 2, 2 goes back to 2. 3 goes to 4, 4 goes back to 3, 4 goes to 1, 1 goes back to 4. So yes, it is of course sigma inverse. Okay, why is this true in general? Well, because of the transpose operation. This was in row 1, column 3. A13 is now in row 3, column 1. Okay, so we can think of it as B31, where B is another name for that matrix. Okay, and so that 3 is sigma 1, so we can think of it as 3 sigma inverse 3. Okay, so therefore the term that we get from B is exactly the same as we get from A. Now, because of this property, any theorem, any statement that we can make regarding the rows of a matrix or row operations will also translate to another theorem concerning columns. So, what did we see? If you have a row of all zeros, you get a determinant of 0. So similarly, if you have a matrix where a column is entirely 0, then the determinant of that matrix is also 0. Okay, so let's crank it up just one little level. Okay, row of zeros, that's kind of easy. Okay, here's something which is not so obvious. Suppose that you have an n by n matrix with 2 proportional rows. So in particular, you could have 2 equal rows. The proportion is just 1. Then the determinant of that matrix is still 0. And of course, we just said if it's true for the rows, it's true for the columns. So if you have a matrix with proportional columns, then it also has a 0 determinant. Okay, so why is this true? So what's going on in this matrix? I see a K over here, and that's 4, 1, 4, 2, 4, 3, 4, 4. Aha! So row 2 is proportional to row 4. Okay? So what is the term that we will get from A? Okay, so we're going to have a sine of sigma, and this is the same permutation that we had before. Okay, so we have A13 over here, KA42 over here, and A34 over here, and A41 over here. Okay, so our sigma is 3, 2, 4, 1. All right, so we don't know anything about these numbers, so that term may or may not be 0, right? So the idea now is, well, can we find an additive inverse for this term? Because after all, a determinant is a summation, okay? So if this is 7, let's say, is there a term, another term, that we can get from the determinant of A that will give us negative 7, so that when we add them together, we'll get 0. Okay, so let's think about that. Oh, by the way, what is the sign of this? So, sign of sigma is 3 is bigger than 2 and 1, so that's 2. 2 is bigger than 1. 4 is bigger than 1. So it is an even permutation. Okay, so actually those are not, that's not the sign, those are the inversions. So the sign of sigma is positive 1. There we go. So we need to get a term from A where we will get negative A13, KA42, A34, A41. Okay, so here's the hint. All right, I need another term where I still have A13, but I can move the K somewhere else. Okay, and what's again, where did this come from? The second row is a multiple of the fourth row. Okay, so I have an A42 here with a K. I can pick this A42 to make another term. Okay, so that's not chosen over here. We chose A41 over here. So, okay, now I need to balance this out. I also need that A41 so that I get the same term until I get a minus sign. Okay, so where will I get the A41? Right there. Oops, sorry about that. Right there. Okay, so there's an A41 over there. Oh, look, it comes with a K. All right, so that is the second term that we need. All right, so I made a copy of A over here, and I boxed those two terms that I was talking about. So compare. I kept the A13. This time I pick KA41. I keep A34, and this time I pick A42 instead of A41. So we get a second term from A to match our first term. So it will have a sign for some tau. And I still have A13, KA41, A34, and A42. Okay, there's a helicopter overhead. Okay, so who is this tau this time? Is it the inverse again? Let's see. So we got to squint. Okay, from row 1 we get column 3. From row 2 we get column 1. From row 3, whoops, wrong place. From row 2 we pick column 1. From row 3 we pick column 4. From row 4 we pick column 2. Is that sigma inverse? 1 goes to 3, 3 goes to 4. No, not this time. Okay, but what do we see? Okay, 3 is the same, 2, 1, 4 is the same, 1, 2. Okay, why are some the same and one different? Some different. I kept the A13. Okay, I kept the A34. So therefore, the 3 and the 4 there are the same. But this time, I reversed. Wait a minute, what's a better word? I switched. I swapped. I swapped instead of KA42, I picked the 42 down here, the A42. Instead of A41, I picked KA41. Ooh. So the effect was I swapped the 2 and the 1. And what did we say in the last video when we saw the two properties of permutations? We already used the first one. We said that the sign of the inverse of the permutation is the same as the original permutation. And this time, if you switch two entries in a permutation, and they don't have to be next to each other, the sign flips. So the sign of tau is the negative of the sign of sigma. So instead of positive 1, we will get negative 1. All right, so we get exactly the same numerical factors, and the signs are opposite. So when you add these together, they cancel out to 0. So of course, this is true in general. Pick any term from A. You can find a matching term also from A that will cancel to get you 0. All the pairs add up to 0. You get 0 for the. Okay, so for this theorem, we're going to introduce a couple of vocabulary words. So these special matrices are seen in chapter 4, which we will actually see later. Okay, so they're called triangular matrices, although you've actually seen examples of them before. They show up when we do row reduction, and when we reach this condition, it looks like we're halfway through finding the REF, right? If these were ones, then we're halfway through the REF. They don't have to be 1 though, okay? So what are these upper and lower triangular matrices. Okay? So we want zeros below what is called the main diagonal of your matrix. So it's called the main diagonal. That's where the row and the column subscripts are exactly the same. Okay, so you have A11, A22, A33, A44. Okay, so who is this entry over here? That is A21. It's in row 2, column 1. So we want that entry to be 0 when the row number I is bigger than the column number J. Okay? Who is this entry? That's row 4, column 2. 4 is bigger than 2. We want that entry to be 0. Okay? So similarly, check it out. Compute matrices transpose. Ooh, so there you go. So similarly, if you transpose an upper triangular matrix, you now get what's called a lower triangular matrix. How do you distinguish the two? Okay, I just had a slip of tongue just now. The way to remember it is the interesting numbers are found in the upper part of the matrix. So therefore, this is an upper triangular matrix. The lower part is boring. Okay, so we don't focus on the boring part. We focus on the interesting part. Boring. So this is a lower triangular matrix. Okay, so what is this theorem saying? If you want the determinant of either one of these matrices, all you gotta do is multiply the entries on the main diagonal. A11 times A22 times A33 times A44, and so on. So in particular, if the upper part is also 0, you get what's called a diagonal matrix. And this is how we write a diagonal matrix in chapter 4. Okay, so don't worry about that right now. Okay, why is this true? Okay, let's walk through the proof. It's actually quite simple. Let's focus on A. Okay, how do I make a term from the determinant? I have to pick something from every row and from every column. Let's use the column approach this time. I need to pick somebody from column 1 to make a term. Okay, well, what if I pick this guy? Oh, sudden death. Okay, as soon as you pick an entry which is 0, it doesn't matter what the rest of that term is going to be. It's just going to get killed by that 0. So that whole term is 0. So the only choice from column 1 that has any hope of surviving would be A11. As soon as you pick somebody, one of these zeros, it's dead. Okay, so I have picked A11. I can no longer pick anybody from row 1 when I look at column 2, 3, and 4. Okay, I have burned row 1 by picking A11. So who can I pick from column 2? I pick this 0. Oh, dead again. So, same principle. If you want your term to survive, the only choice with any hope of survival would be A2. Okay? It's kind of like going through one of those TV shows where there's a challenge and you want to survive each challenge. Okay? So don't pick a 0. You want to stay alive. Okay. So I picked A11, A22, so I can no longer pick any of these entries when I look at column 3 and column 4. Okay, don't pick the 0, pick the A33 instead. Okay, so now I can't use any of those terms when I look at the 4th column. So, no choice. I need to choose A44. But wait, there's more. Remember, there is still a sign sigma in the determinant formula. So we're not quite done yet. Okay? But who is the sigma in that term? Column 1, column 2, column 3, column 4. Do you see any inversions? No, of course not. Because that's not just any permutation. That is the special iota, the identity permutation. So, of course, the sign is positive 1, and that gives us the determinant formula that we wanted to prove. Okay, so we're getting closer to our method to find a determinant using row operations. So let us now look at elementary matrices, which are, of course, produced from the identity by performing exactly one elementary row operation. So if your elementary matrix is obtained from the identity by multiplying row I by k, and remember k cannot be 0. Here's an example where row 2 is multiplied by 7. Then the determinant of that elementary matrix is just k. Okay, so this determinant, we can answer it right away. That determinant is 7. All right, now why is that? Well, we just talked about upper and lower triangular matrices and diagonal matrices. This is an example of a diagonal matrix. So the formula said just multiply the entries in the diagonal. 1 times 7 times 1 times 1 is 7. Easy. So of course, if that 7 were k, or if it's found over here, that determinant would just be k. Let's go to the third operation, because this is easier. Let's add k times row I to row j. Then the determinant of that elementary matrix is just 1. All right. So instead of the 7 being here, I put a 7 over there. Okay, just to mess with you a little bit. Okay. That's now a type 3 elementary matrix, a sum. Okay. So what did we do? To produce this row, I have to add to row 1 7 times row 3 to make that 7. Okay, so is that a special matrix? We still see zeros down here. So the interesting parts are up here. So that is an upper triangular matrix. The formula says, again, just multiply the entries on the diagonal. So that determinant is just 1. Okay, and of course it doesn't matter if that 7 were somewhere else. It could be over here instead, and that could be a negative 3. That's now a lower triangular matrix, and that determinant is still 1. Okay, so the second kind, the swap. Yeah, this is the one where we have to think a little bit. Okay, so we're going to use the same principle that we used to prove that theorem about triangular matrices. We have to pick somebody from row 1 and from column 1. Okay, so this time, let's just walk through the rows as usual. I need to pick somebody from row 1. Okay, don't pick the zeros or you will die. So you want to pick that 1. Okay, I'll write it over here. Okay, I have to pick the 1 from the first entry, first row. Okay, so now on the second row, I cannot choose anything from column 1, but that's okay. I don't want that 0 either. The only entry that will help me survive is, again, that 1. Okay, so we want that 1 and so on. Okay, so again, luckily, I don't want this 0 in row 3 or that 0 in row 3, column 1 and column 4. I want that 1. I want to live. So I pick that 1, and of course, in the last row, I have no choice but to pick that 1. Okay, and of course, this is possible because in the identity matrix, the original identity matrix, a 1 appears in every row and in every column. Okay, by the way, maybe I should have started with this. How did this come from the identity matrix? Okay, so that's where it should be. That's where it should be. That's not where it should be. That's not where it should be. Oh, if we swap these two, that's how you get that elementary matrix. Okay, so speaking of swap, what is the sigma that we get from choosing these four ones? I need column 1, I need column 4, and then I need column 3, and then I need column 2. So when we did the last proof, iota came out. 1, 2, 3, 4. That's not iota. However, what happened? 1 and 3 are where they should be. 2 and 4 got switched. So we use that theorem once again. If you switch two components in a permutation, you get a permutation with an opposite sign of that original permutation. Okay, so this will be the negative. So the sign, let's say it correct. The sign of sigma will be the negative of the sign of iota. And we said the sign is +1, so this sign is now -1. Okay, so that -1 gets multiplied to that product, and of course we get negative. Okay, so that determinant is negative. Okay. Oh, I almost forgot. So before we move on, I want to point out that in a type 1 operation, k cannot be 0. And -1 and 1 are obviously not 0. So in all three kinds of elementary matrices, in all three types, the determinant is not 0. Okay? And remember that I mentioned that one of the main theorems that we're going to prove about determinants is that it's basically a litmus test. A matrix is invertible if and only if its determinant is not 0. So these determinants are not 0. So obviously all of them should be invertible. Okay, so we can now move on to the effect of an elementary row operation on the determinant of a matrix. So here's the setup. Suppose you have A as an n by n matrix, and then you obtain B from A by performing one elementary row operation. So if you do it by multiplying row I of A by k, a non-zero number, then the determinant of B is k times the determinant of A, your original matrix. If you exchange two rows of A, then the determinant of that new matrix is the negative of the determinant. If you do a type 3 operation, if you add k times one row of A to another row of A, then you don't change the determinant. The determinant of the new matrix is still the same as the determinant of A. Okay? And again, because a theorem remains true if you replace row by column, this now allows us to perform elementary column operations on a matrix. So if you multiply column I of A by k, this formula still works. But notice, what did I just point out to you a couple of minutes ago? The determinants that we got in the last theorem were k, -1, and +1. Okay? So this theorem is a special case of the other property of determinants that I also have mentioned to you, that the determinant formula is multiplicative, not additive, but multiplicative. How do we think of this using matrix products. So remember that one of the special properties of elementary matrices is that if you multiply a matrix to the left by an elementary matrix to get another matrix B, you would get B by performing on A the same elementary row operation that you performed on the identity to produce E. But what did we say? These determinants for these types of operations were respectively K, -1, +1. So what these three parts are telling us is that if B is an elementary matrix times A, then the determinant of B is the determinant of B times A, because B is C times A. But this next step is now the best part. We can rewrite this as the determinant of B times the determinant of A, right? So in the next video, we will be generalizing this to any two matrices. What happens if you multiply a matrix by a scalar? Okay, so you don't just multiply one row by K, you multiply all the rows by K. Now each of those products will give you a contribution of K. There are n rows, so in all you have a factor of K to the n multiplied by the original determinant. Oh, by the way, K should not be 0, but what happens if you multiply A by 0? You will get the 0 matrix. Lots of zeros there. The determinant is exactly 0. And on the right, you have 0 to the n is still 0 times the determinant of A. So it doesn't matter if K is 0 or not. This equation is still correct. Okay, so let's go through the proof over here. We have an original matrix A, and what happened? I multiplied the third row by K. Everything else is the same. So, if you understand one term in the formula, you understand the entire formula. Let's pick out the same term that we picked last time. If I choose the same corresponding entries in B1, what's going to happen? A13 is the same, A22 is the same. A34 now has an extra K. A41 has an extra K. No, A41 is exactly the same. Okay, so all we have is an extra K from row 3. Okay, well, you have to pick an entry from row 3 for every term. So therefore, every term has an extra K. You can factor out that K. So the determinant of B1 is K times the determinant of A. A swap is almost as easy. Okay, so here we have the original matrix. And what did I do? What have you done? Okay, row 1 is the same. 4, 1, 4, ooh, that looks like row 4. Row 3 is the same. Ooh, that looks like row 2. Oh, I swapped row 2 and row 4. Okay, so now, what is the corresponding term from B2? Well, keep the A1 3. I want that A4 1, so I have to pick this number. Keep the A3 4. I want that A2 2, so I need to pick that number. Okay, so what have we got here? In the first matrix, the permutation that we have is 3, 2, 4, 1. Okay, in our B2, the tau that we have is 3, 1, 4, 2. Okay, does that sound familiar? Yeah, we switch 2 and 4. Okay, so therefore, the sign of tau is the negative of the sign of sigma. Okay, so we can choose the terms so that every term in B2 that we pick is the opposite sign of the corresponding term in A. So therefore, we reverse every sign in the determinant for A. We get the negative of the determinant of A for the determinant of A. Okay, unfortunately for a type 3 operation, it's not quite as obvious as the type 1 and type 2. We're going to need what's called a lemma. And a lemma is just a theorem which is used to prove a more important theorem. So in this case, that theorem is the formula for a type 3 row operation, that you don't change the determinant of the matrix when you perform a type 3 operation on it. Okay, so we have to read this theorem very carefully. Let A, B, and C be n by n matrices that have all entries equal. All entries have to be the same, except for the entries in row I, in one row. However, row I of C is the sum of row I of A and row I of B. Okay, so all entries are the same, except for one row, the same row on all three matrices. And it so happens that row I of C is the sum of row I from A and B. Then what's going to happen? The determinant of C will be the sum of the determinant of A and the determinant. And read that very carefully. This is not saying that the determinant of C is the determinant of A plus B. No. It's the determinant of A plus the determinant of B. Okay? So let me warn you that in general, the determinant of A and B plus the determinant of B and the determinant of A plus B is not true in general. Sometimes it's true, but in general, it's not true. Okay? So that is the correct right side of this lemma. Okay. It's actually easy to see once you understand what it says. So I made these three matrices, and they should all be the same except for one row. Okay, row 1's the same, row 2's the same. Ooh, row 3. Okay, so I use different letters for B. And in row 3 of C, I have to add row 3 of A to row 3 of B. Okay, row 4 is exactly the same. All right, so again, you think of the determinant one term at a time. Okay, so let's start with the determinant of C. We will need the sign of some sigma. Okay, and then we have to multiply these four terms together. 3, 82. Let me put parentheses. 834 plus 84. And finally 841. Okay, and then we're going to feel a little bit foolish because what can we do? Well, we have this thing called the distributive property. So I will distribute this term so that 834 is by itself and E34 is by itself inside the parentheses. Okay, so that step is just the distributive property from chapter 0. Okay, now wait a minute. Where do I see A13, A22, A34, A41? Ah, right there. And it's the same permutation. Similarly, this is A13, A22, B34, A41. Ah, that's the corresponding entry in B. Okay, so what's the bottom line here? Every entry in the determinant for C can be distributed into a sum of an entry from the determinant of A and a term from the determinant of B. If you can do it with one term, then you can do it to all terms, and therefore the determinant of C is exactly the same as the determinant of A plus the determinant of B. Okay, so now we can prove the formula for type 3 row operation. So I took the original matrix A, and then obviously I changed row 3. Okay, so I have A31 plus K A11, A32 plus K A12, and so on. So it looks like I added to row 3 K times row 1. Okay, so B3 will take the place of the matrix C in our last theorem, in the lemma. Okay, so what I want to do is, I want to write the determinant of B3 as a sum of two determinants. Okay, so what did the lemma say? If I can break down this matrix into two matrices so that everything is the same except for row 3, then I can apply that formula. It will just be the sum of the determinants of those two matrices. Okay, so what would be the logical way to split up this matrix in two in the format of that theorem? Well, I can keep the A's in one matrix, and I can put the K times A's into the second matrix. Okay, and of course, that's already prepared for us down here. Creative scroll. All right, so there you go. I have A31 over here in A, and I have the K's over here in B. And that is the original matrix A. But we have this matrix B. Okay, so that's new, right? So the lemma says, let's put that here. By the lemma, by the power of the lemma, the determinant of B3 is the determinant of A plus the determinant of B. Okay, but what do you notice about B? I have these K's times A11, A12, A13, A14. Wait a minute, that's row 1. Okay, so one of our earlier theorems says that if two rows of a matrix are proportional to each other, then its determinant is 0. Okay, so the determinant of B is 0. So therefore, the determinant of B3 is exactly the same as the determinant of A. So the bottom line is a type 3 row operation or column operation does not change the value of your determinant. Wow, so we're almost at 54 minutes. So finally, we get into a big numerical example. We are going to find the determinant of this matrix A. Okay, so what are we going to do? We will perform row or column operations until we get a triangular matrix. You want it to be upper triangular, lower triangular. It doesn't matter. Okay, we know what to do at that point. Just multiply the diagonal entries together. But as we perform the row operations, we have to keep track of swaps. Okay, but fortunately, they cancel in pairs. Every time you swap, you have an extra -1. But if you swap again, those two cancel out. Now, how about the scales? Okay, so you have to keep track of them. What I do is I have a little scratch work on the side. I say, pay for this later, something like that. I owe the determinant of A, these factors. Fortunately, type 3 operations are free, so we don't have to keep track of them. Okay, and remember, I kind of felt bad the last time when we did an inverse, and we didn't have any scales or swaps, I think. So I think we had one scale and no swap. Okay, so this time we will have scales and swaps and lots of sums. All right, let's get to it. So here's our example. And I hope you notice that we have some 2-digit numbers in our matrix. And check it out. Every number in row 2 is divisible by, yes, 4 is our biggest factor, common factor there. And every number in column 3 is divisible by 7. Okay, so we're going to do scales. Let's start with scales. Okay, actually, let's start with the answer. Let's cheat. Compute matrices. Determine. That's ginormous. 24,248. Okay, so what did we say? Let's do a scale. Okay, so you know what? What I'm going to do is I'm going to take row 2 and I will divide everything by 4. Okay, so I'm just going to copy row 2, divide that row 2 by 4. We get this much smaller numbers. Okay, that will now be the new row 2. Okay, so let's call it B1. So B1 will be the original matrix A, where I replace row 2 with this. Okay, but of course the determinant of B1 will not be the same as the determinant of A because we did a scale. Okay, let's look at the relationship. Compute matrices determinant. 6062. A lot smaller. Why? Because I owe the determinant of A 7. Okay, I'm sorry, no, 7 is later. 4 for now. So if we multiply 4 here, then, yep, we get the original determinant. Okay, so let's write that down. I owe det A 4 for now. Okay, so that determinant is smaller. That's a good thing. Let me erase that. So we will find that determinant in a minute or 5. Okay, so what did I say? So next, let us scale column 3 by 7. Okay, so let's take this and we divide everything by 7. And we get, again, much smaller numbers. So I will get a new matrix, B2. So B2 will be, in B1, I will change column 3. Okay, so that determinant, again, changes. Okay, we said that B2 has determinant, oh, I erased it, it was 6,000 something. Okay, so what about B2? Compute matrices determinant, even smaller. Okay, so while I'm at it, I also have to pay for that 7 at the end. Okay, so now, what's the net change? I have to multiply by 28. And yep, that is the original determinant. Okay, so I hope you see what I'm doing, right? You can definitely make your numbers a lot smaller by doing scales, okay? Someone gives you a matrix with fractions, take out those denominators. Okay, so this time, if you factor out a 1/4, now you owe determinant A a 1/4. Not 4, but 1/4. Okay, so now let's do some swaps and some sums. Okay, we have a beautiful -1 over here. So I will swap row 3 and row 1. Okay, so you know what? I'm going to stop giving names to the matrices. Okay, I will make a copy and I will put row 3 into row 1, but I can take the original row 1 and put that into row 3. Okay, I did a swap. So therefore, I owe a -1. If I do another swap later, I can just erase that -1. Okay, and now we will do type 3 row operations. Okay, so we'll take row 2, we will add 4 row 1, this, row 3, add 5 row 1, we get this, and row 4, we will add 3 row 1, and we get this. Okay, so now those are elementary type 3 elementary row operations. They don't change the value of your determinant. You will change the matrix, but you don't have to change the determinant. And you know what? Let's check. Okay. What is the determinant that we get here? Compute matrices determinant -866. So remember for D2, I believe it was positive 866, but we did the switch. Compute matrices determinant, and yep, it was positive 866. Excellent. So now, anything we can scale, yeah, I guess we can divide by 2 over here. Oh, but wait a minute. We have an 18 there. So let's do another type 3 row operation. Whew, I did not see that coming. So I will take row 3 and I will add 6 row 4. And we get, nice. So that's a 0. And what about the 17? We can make a 1 or a -1. Okay. If we also do 6, we will get -18 plus 1 plus 17 is -1. Okay, so cool. That is our next step. And I can recycle this. And we got that. All right. So now our next matrix is going to be, this goes into row 3. You have to make sure that you put them in the correct row. Otherwise, that would be a switch and your sign would be wrong. Okay, so that is where we have what we have so far. And now we can get rid of the -3. Okay, and you know, I just realized I'm not doing any column operations, so I apologize for that. So let's take row 4 and we will subtract, is that the correct thing? Yes. We will subtract 3 of row 2. So that's going to be a +3. Okay, so there you go. That is now the new row 4. Okay, so getting close, getting close. Let's check. Is the determinant, where are we? I believe -866, right? Compute matrices determinant. Yep, negative 866. So far so good. Okay, so we're close, except we have these ugly numbers. Okay. Yeah, you know what? Let's just bite the bullet. We have a computer to do the dirty work. So let's divide row 3 by 32. Okay. And because of that, now I owe a 32. Okay. Think of dividing out as factoring out. Right? So therefore, we have this new row 3. And now we will clean up our negative 67. And we have row 4 plus 67 times row 3. Okay. So that will be the new row 4. And there we go. We have reached a triangular matrix, an upper triangular matrix. Okay. So now we can complete a formula for the determinant of A. Let me speed up a little bit more. Okay, it still fits. The determinant of A will be, so I owe all this much, so let's put that here. And then I multiply these together, minus 1, plus 1, 1. I just multiply by this. So I get negative 433 by 16. Multiply that together and we get, boom. That is, of course, the determinant of the matrix that we checked from the beginning. Okay, I knew this was going to happen. This is our longest video so far, and I thank you for your patience. I hope that you enjoyed it in any case. So, this is Rude Socrates signing off. You will find me on Facebook, and you will find 4th edition on Facebook and at kendallhunt.com. So, until our next video, I hope you enjoy the rest of your day.